The mic working? Yes.
Welcome everyone. We're going to go ahead and get started now. This is session 7C, storage optimizations in software. We will start our first speaker, and we also have this working on operating systems, and it's on market for our research and engineering.
Hello everyone, my name is Emil Tsalapatis, and today I'm discussing our work on MemSnap micro checkpoints. So, in a nutshell, this talk is about providing persistence as an OS service. Applications persist their data using user space mechanisms that are built on top of the file API. However, these mechanisms are invariably difficult to write, slow, and worst of all, error-prone. We propose an alternative API that handles persistence as a first-order primitive and makes persistence easy for applications by handling it in the kernel. We propose a novel single-level store mechanism for providing this persistence. This single-level store mechanism unifies memory and storage into a single tier to simplify the semantics of persistence. The result is that we make it not just easier, but also faster to write persistent applications. But let's first talk about what persistence is. Persistence is the ability of data to survive an interruption. That can be an application crash, kernel crash, or a power failure. Applications persist the data by having an extra copy on the disk. In case of a crash, we can create a new instance of the application that reads in the data and continues executing. This means that the on-disk copy of the data must get in sync with the main copy of the data in memory. This is done using the file API. Applications organize their data into files, update those files using the file API, and then propagate changes to disk using fsync and msync. So far, so good. So what's the problem here? The problem here is that indirectly, the file API is responsible for data loss. It is very difficult to get the file API right. Invariably, once in a while, we get tools that automatically check the consistency of persistent applications. And the end result is that we always find active possible data loss bugs in existing and widely used software. Even mature applications can use data because they somehow misuse the file API. Databases like SQLite, RocksDB, and PostgreSQL have had their fair share of data loss bugs over the years. The database community has even reached the conclusion that MMAP is too difficult to get right for persistence, and therefore they only use explicit file I/O. We propose that the core source of all these data loss bugs is not the application developers, but it is the API itself, and we should find a better alternative. So this is where MemSnap comes in. MemSnap is an API based on a single-level store OS architecture. It unifies memory and disk into a single storage tier from the application's point of view. The application only sees crash-tolerant memory, in that it can have all its data in memory and assume that the system never crashes. When the application makes a modification to the in-memory dataset, it just calls MemSnap persist, which will transactionally commit those changes to the disk. MemSnap takes care of all the steps necessary for that. The end result is that we don't just simplify, but speed up existing applications. We are an order of magnitude faster in persisting random I/O compared to the file API. And in fact, persisting random I/O with MemSnap is faster than persisting sequential I/O using fsync. We will see how we achieve these numbers in this talk. So MemSnap is an evolution of a single-level store concept that uses application checkpointing in order to persist our entire applications through a crash. However, existing single-level stores cannot be a replacement for the file API because they cannot checkpoint at a quick enough granularity without either user space mechanisms like Rakeeb logs for Aurora or specialized embedding hardware for 3SLS. MemSnap does not require specialized hardware and is able to persist at the file granularity without user space walls. So the main challenge in building MemSnap is in being able to provide in-place update semantics to the application and be able to persist it efficiently on the disk. Currently, applications cannot just modify the data in memory and then flush it out with fsync, because if the write gets interrupted by a crash, then we will cause data loss by half writing the data on the disk. We instead use things like Rakeeb logs, where we declare our intent to modify the database file first in a separate append-only journal on the disk, and then eventually propagate those changes to the main database file with a second I/O. Rakeeb logs are safer, but are still difficult to write, and are also expensive since they duplicate I/O and also add latency. MemSnap, in contrast, provides in-place update semantics. With MemSnap, we organize data into MemSnap regions. These are very familiar to the developer because they essentially, for all intents and purposes, function like memory map files. The only difference is that these MemSnap regions have a set virtual memory address into which they are mapped for every process across crashes. This is so that we can provide in-memory update semantics. Since we do not serialize data into files, we are also storing pointers in these regions and we need them to be valid through a crash. MemSnap uses a copyright object store in order to provide the illusion of in-place updates to the application. For every MemSnap persist call that the application makes, they will create a checkpoint that we propagate onto the disk. This checkpoint is applied in a copyright fashion to the existing dataset. If we crash, then we have not corrupted the existing data. If we succeed, we have provided the illusion of changing data in place from the application's point of view, since copyright is not visible. Another challenge that MemSnap handles is tracking the dirty set of the application without help from the application itself. Tracking the data is actually quite complex from inside the application, considering we need to interpose on every access to the data in a file. Moreover, this is complicated by the fact that multiple threads might be doing multiple concurrent transactions to the dataset. MemSnap is able to transparently track the changes to the dataset per thread at a page granularity. MemSnap initially maps all data into an address space as read-only because it's clean. And every time a thread tries to write to a clean page, it will declare and write a minor write fault. MemSnap will then interpose on the fault and mark the page as writable, but not before adding it into a per thread dirty set list in the kernel. The upshot of this is that when the application is done with its modification, MemSnap already has all the pages that have been dirtied in the region and is able to flush them out efficiently to the disk. So this is another challenge that we solve for the file, when the file API fails, but which we solve. The file API normally cannot handle flushing small, sparse datasets. And that is because fsync and msync are made either to flush entire files or to flush contiguous regions in a file. However, with in-place update semantics, we have randomly distributed datasets which cannot be flushed efficiently. MemSnap is able to do this since we have already pre-tracked these pages. We can flush them in parallel and compose them into a checkpoint on the disk. Moreover, MemSnap then reapplies read protection to these pages flushed so that a subsequent transaction will also be tracked. This is actually a major bottleneck if done incorrectly, and we have created our own read protection mechanism in the kernel. We take advantage of the fact that we know exactly which page table entries to turn from writable to read-only. And this is because these are the same entries that we have turned from read-only to writable over the course of a transaction. We have put these PTEs into a trace buffer, and then we are able to just traverse the trace buffer and one by one turn them back to read-only. This is way faster than the alternative, which is either scanning each PTE regions in the page tables to find the dirty pages, or doing in-place updates to the page table, traversing it from root to leaf every single time. The last challenge we solve is that of multithreading. It is perfectly valid for the file with the file API for a thread to modify in-flight data that is being committed by another transaction. As a result, of course, this can cause data corruption to the in-flight data. We handle this using copy and write. Every time a thread tries to write to data that is being flashed out, it will incur a minor page fault. But instead of marking it as writable, MemSnap will instead create a copy of that page dynamically and give it back to the right thread. That means that the right thread can continue its in-memory transaction while the committed data is still being flushed out, safe from modification. So we have seen that MemSnap provides significant performance benefits for micro benchmarks, but these micro benchmarks directly translate to performance benefits for real workloads. So we have modified 3 databases that are very different and span the design space: SQLite, RocksDB, and Postgres. For all 3, we have removed code while gaining performance speedups. We have described all 3 of them in the paper, while here we will mostly be focusing on SQLite. SQLite has a very representative of databases rolling checkpoint persistence mechanism. Each transaction is persisted by being written to a write-ahead log. This write-ahead log eventually becomes too large and must be flushed into the main database file so that it can be truncated. In that case, we update the main database file with the new data and flush it out with a large random I/O called a SQLite checkpoint. Instead, with MemSnap, we replace this write-ahead log with in-place modifications followed by an MemSnap persist. This also means that we can remove the SQLite checkpoints from the code base. The end result is that we get 4x better latency for persisting transactions over the baseline. This is due to 2 factors. First of all, as we have seen, we have better persistence latency by 2x compared to the wall, since we persist random I/O 2 times faster than the file API persists sequential I/O. The second factor, the second speedup, is due to removing the checkpoint operation. The checkpoint operation is relatively rare compared to individual transactions, but it is disproportionately expensive and affects average latency. This becomes even more obvious if we look at tail latency, where we gain 4x better latency. This is because we have removed the main driver of tail latency from the baseline, that of SQLite checkpoints. So we have more details on how we use MemSnap to modify to speed up applications and simplify them in the paper. We also have an explanation on how this is possible for arbitrary databases. The code is available online, and I'll be happy to answer any questions. Thank you for your time.
Okay, we've got time for some questions.
Hi, I am Sudarshan from Rutgers University. This is really nice work. So I had one question on the write-ahead log. One of the reasons for using a write-ahead log is that it provides kind of 2 guarantees. One, it provides kind of like a serialization between multiple threads updating the log. So if there are 2 threads contending, you can still kind of serialize updates to the log. That's first guarantee. The second guarantee is that by file system semantics, if a block K is committed in a write-ahead log, you could safely assume that K-1, K-2 is also committed. And that's the guarantee that POSIX file system provides. I wonder, how do you provide that guarantee by removing write-ahead log?
So we do this in the copy and write object store. Like the copy and write object store does provide a serial ordering of commits. And in fact, this is why it is safe to start, like MemSnap can commit synchronously or asynchronously. So you could do an asynchronous commit and you're absolutely certain that if a commit that happens after will still be ordered after the commit that is in flight. So essentially we do this in the copyright object, so we just hide it from the user.
Right, but if there are 2 threads that are writing to some random locations.
Oh, I see.
Right, so even if you do copy on write, you will probably commit one write, but you'll not be able to commit because they're writing in some random location. A write-ahead log serializes that update. Right, so that's what maybe we can take it offline, but
yeah, maybe we should talk about it online. But
sure,
like, are you saying like maybe if they're writing to the same location and then which one will persist?
If they're looking like write-ahead log serializes updates, it makes everything to some extent sequential when you commit it, right? So when you have random writes and you kind of like
Mhm.
even to copy and write.
Yeah.
There is no guarantee that two writes can be kind of like made sequential. That's my point. We can
I see. Yeah, let's talk about offline. Like essentially, like just to maybe this will help. If the database commits essentially is serializable and commits in serializable fashion, we retain this guarantee.
Got it.
Across persistence.
Got it.
Thank you very much. No, thank you very much. Yeah. So it's all good.
Hey, Matt from TUM. I wanted to ask you, you've shown that your solution is better for latency. I wanted to ask, what's the memory overhead of all this bookkeeping compared to other
The bookkeeping for tracking, for example, the
you
paper.
have some data structures inside to all do.
Oh, these are so
Compared to the usual, how does it compare?
yes, so these are minor, and they're minor mostly because first of all they're just lists like in the kernel, and they don't really have an extra overhead in that we don't use any complex data structures. Like for example, the trace buffer is up until megabytes of data, and they can handle as large transactions as like some megabytes of transactions. For larger transactions, we do have fallback paths. So it is really configurable to the user if you'd like to do, I don't know, like gigabyte transactions. So in general, the space usage is not a factor, especially compared to the actual data that we are storing out.
Okay, thanks.
Great. Let's thank Emil again. Next speaker is Tsun-Yu is a staff at Academia at Seneca, and is currently looking for academic positions here in.
Okay, so hello. Hello everyone. So my name is Emil, and today I'm going to present the work that is the Grafu unleashing the full potential of feasibility computation for our course Synchronous growth processing. So to begin with that, the graph is actually a powerful data structure to record the relationship between entities in different fields, and this also makes that the prefetching become an important topic to study that how we can efficiently analyze the graph data. So there are many ways to support the graph processing, but the article graph processing can actually provide a cost-effective solution with the help of the storage. So it keeps the massive graph data in the storage and load a small part of the graph data into the memory to process when necessary. And the classic data structure to keep the graph data inside the storage is to use the grid-based structure. So the grid structure will first divide the vertex into a multiple disjoint partition P. And based on the partition result that we further divide the edge data into the grid. So each grid contains edges where all the source vertex belong to one partition and the destination vertex belong to another. So processing a grid can enjoy a good located access because as we can see here that if a grid is being processed, that we don't need to access the entire virtual data, but then we can only confine the access to two partition onlys. So during runtime that the graph system will process one grid at a time by loading them into a memory. But however, because the storage I/O is slow and is typically a bottleneck for this type of graph system, so how to minimize the I/O becomes our main objective in this work. And another important feature for the graph system is to provide a user a semantics. And with this semantic, that user can expect how the graph system can process a graph, and therefore that user can implement the graph algorithm correctly. And in fact, that the synchronous semantic is actually a pretty famous one, which is widely adopted in the many graph systems. So this semantic can require that the vertex update value can only be from the vertex value from the previous iteration. So in other words, as we can see, so in the example in the right figure, that to update the vertex value of the iteration t+1, we can only use the vertex value from iteration t. And once the iteration t+1 receives all the updates from the iteration t, then those vertex value of the t+1 become ready. So it means that we can move from the graph processing to the next iteration. So the normal processing just keep working iteration by iteration until the graph algorithm converge. And the advantage of using this kind of synchronous semantic is that it can allow the easy programmability for the users. So this is the first advantage. And then the second one is that it can further allow us to perform some easy and clear analysis to the implement graph algorithms. And when it comes to the overhead, then we can observe that the normal processing will load 100% of the edge data in each iteration. So so far we have seen an example of the normal processing. So in the following slide, I will show that how the feasibility computation can not only reduce I/O but also ensure the synchronous semantics. And to better explain how it works, that we will show a simple example here. So we consider this simple graph where the vertex C has two neighbors, the vertex A and vertex B, and we have one outer neighbor that is the vertex D. So suppose that the vertex C first receive all the vertex update from its neighbor, that is the vertex A and B. Then in such a case that the vertex value C in the iteration T plus 1 become ready in the iteration, and because there's no other updates from the iteration T can affect the value of C anymore. So by doing this one, then the value of vertex C become ready. So the next, when we load the edge of CD into the memory, then we can perform not only the normal computation but also the feasibility computation. So the normal processing here means that the update from the vertex C to vertex D between the iteration T and T plus 1. And the feasibility computation means the update from the C to D between the iteration T plus 1 and T plus 2. So after doing all that, we move to the next iteration, that is the iteration T plus 1. Then we don't need to load the edge of CD anymore because it was already processed in the previous iteration. So this is how the feasibility computation can help to reduce I/O while ensuring the synchronous semantics. So right now we know how the feasibility computation works and also its benefit. So this slide will further model the theoretical I/O improvement of using the feasibility computation. And we can simply formulate the I/O improvement by calculating the I/O amount of two continuous iterations. So for these two continuous iterations, we will call them the iteration T and the iteration T plus 1 for simplicity. So here we assume that in the iteration T, we will load the entire edge data into memory, and then we can perform the feasibility computation on the E prime number of edges. So in the iteration T, the I/O overhead is E. And for the next iteration, the iteration T plus 1, we only need to load the E minus E prime number of edges. So the E plus E minus E prime indicate the I/O amount of two iterations with the feasibility computation. And on the other hand, the 2E here indicate the I/O amount of the two iterations required by the normal graph processing. So after introducing this equation, that we can easily obtain the optimal I/O improvement. So because the value for the E prime should be between 0 and E, so we can easily get the maximum value by letting the E prime is equal to E. So the maximum value here what we get is a 50% of I/O improvement. And the physical meaning of letting the E prime is equal to E indicates that we assume that all the loaded edge can be processed with the feasibility computation. So in the conclusion of this page, when more edges are processed with the feasibility computation, then we can get a higher I/O improvement. And the optimal I/O improvement we can get is 50% according to this equation. So, however, is that the stable work in this direction cannot well utilize the feasibility computation, and it leaves some room of improvement. So in this motivation, we will run the PageRank algorithm on the two graph, that is the Twitter and the Friendster. And we also run with the grid graph and the Lumos. So the grid graph is actually a baseline system which just work with the normal graph processing. And the Lumos is improved over the grid graph with the feasibility computation. And we can observe that there are two issues in the Lumos. The first one is that the Lumos fail to reach the optimal I/O improvement. So we can observe that the I/O improvement for the Twitter is only 39.6, and for the Friendster is 26%. And this is because the Lumos can only process a subset of the edges. So The second issue is that, so given that the IO improvement cannot reach the optimal value, its execution time improvement of rumors is even worse than IO improvement. So we can see that the execution time improvement is only 20.3% for the Twitter and 40% for the Friendster. So, to this end, that this work presents a system called a Grafu, the Grafu system, which aims to unleash the full potential of visual computation by presenting multiple designs. And this design includes the elevating execution order, the conditional barrier, grid carving, and the fully external processing. But due to time limit, we only focus on the two main designs in this presentation, which are the elevated execution order to enhance the error reduction, and the conditional barrier to improve the filtration. And these two are the main designs to improve the execution time of the graphic. Okay, so we first introduce the elevated execution order. So it helps the Grafu to reach the IO improvement that is close to 50%, which is the optimal value that we just mentioned before. So the basic idea about this execution order is to use the forward execution order in the iteration and the backward execution order in the even iteration. So here we show an example of how this elevated execution order works. So the purple number in each grid indicate the execution order, and the dark yellow grid means that we can process the grid with the visual computation, and the light yellow grid means that we can only perform the normal processing on that grid. So in this first situation, we will use the forward execution. We will use the forward execution order, and we will load the 100% of the edge data. But right here, we're not going through the detail of how the data dependency here because it will take too much time to explain. So if you're interested, please see the paper for more details. But in general, we can see that the grid in the upper triangle can be executed with the visual computation. And so this grid can be skipped in the next iteration. So following in the version 2 that we only need to load the grid in the lower triangle. And because we use the backward execution order, so all loaded grid can be performed with can be processed with the visual computation because only the data dependencies are actually satisfied. And we use the X% to denote the total size of the grid of the lower triangle. So in the third iteration, we use the forward execution order again, and this time we only need to load the grid of the upper triangle, and all of them can be processed with the visual computation. So the IO overhead for the third iteration is 100 minus X%. And for the following iteration, they will follow the same pattern of the iteration 2 and the iteration 3. And therefore, except for the first iteration, which will require 100% of the edge data, the rest of the iteration we only need 50% of the edge data per iteration because they require 100% edge data for every 2 iterations. So for 1 iteration, then they only need around 50% of edge data on average. Okay, so the second design is the conditional barrier. So the conditional barrier is presented to improve the third iterations. So when we're using the traditional barrier, that we will set the barrier at the end where we create a visual value. But with the traditional barrier, then we have to wait the other thread to reach the barrier so that we can start the next segment of the task. So this will somehow degrade the third iteration. So the conditional barrier is actually proposed, and the conditional barrier can actually be removed if we found that the data dependency will not be violated. So the conditional barrier is proposed to ensure the data dependency while improving the thread iteration because we can alleviate the overhead for waiting for the solo thread. Okay, so this slide shows the event setup. Here we just compare the graphic against the grid graph and the rumors. And for the iteration that we showed execution time, we evaluated the execution time here. So overall speaking, we show that the grid graph can actually improve the rumors by 21.4% in IO and 23% for the execution time. And to justify the benefit of elevated execution order, we can see that the graph can actually improve the grid graph by 47.4% in IO, so which is close to the optimal improvement that we just mentioned about, which is the 50%. And to justify the design of the control barrier, we can see that the Grafu without control barrier, which means that we implement the Grafu with the transfer barrier. We can see that they're mostly same in IO because they are all used at the potential order. But the control barrier can actually improve the screen time by around 10.6% on average. And so conclusion that this work with the Grafu system, which aims to unleash the full potential future with the computation. And our iteration also demonstrate that the Grafu can justify this claim. And that's all my presentation today. Thank you.
Okay, any questions?
Hi, thanks for the talk. I'm Xizhe from UC Real Estate. Yeah, I saw in your work you used a strict a synchronous semantic. Yeah, I think which is a very strict form. But I think there are some other graph frameworks that use the bulk synchronous parallelism or the BSP, which is kind of a relaxed form that you can have some asynchronous inside each iteration. Yeah, so I wanted to ask how does your work handle that situation, or it's not considered here?
So based on my understanding, the synchronous semantics, yes, we mentioned here is actually the same as the bulk synchronous. Yeah. So as for the asynchronous one, because the synchronous semantic at hand is actually a pretty it actually provides some easy programmability and actually provides some easy analysis for the user to do some. So for some algorithms that if you find out that a synchronous semantic can actually achieve for faster convergence, then of course then they should use the asynchronous semantics.
Yeah, I see. Thank you. Yeah, the different traits for different applications. So yeah, thank you.
All right, great. But I think
We'll connect here. Right?
great. Okay, so now bring us to our third speaker of the session, Shalini Garlic from Rutgers. And I just wanted to add here that the co-first author, John, so from Rutgers, PhD student looking for a job and comes extremely highly recommended. Especially in kind of.
Thank you. All right. Hello, everyone. My name is Shalini. Let me get you excited about our work. CrossPrefetch, accelerating I/O for modern storage. And this is joint work from Rutgers, Samsung, University of Utah, and Microsoft. Okay. Now we all know that the storage is getting faster. For example, the newest of SSDs take up to 10 Gbps throughput for sequential reads. Large storage-bound applications have complex I/O access patterns, and there has been a lot of work in improving file system performance, including implementing new file systems for modern storage, for example, F2FS, XFS, and so on. In this work, we find that prefetching, for example, prefetching as file system optimizations are still lacking behind in this context, and this leads to loss in performance for the application. Okay, so CrossPrefetch addresses these challenges in prefetching by providing a coordinated approach between the runtime and the operating system, by improving visibility of the prefetching state. And we show that even with well-tuned applications, CrossPrefetch helps these applications get up to 3.7x I/O performance improvement. So let's start by understanding how the file system works today. Okay, applications issue system calls like read or read ahead to the operating system. The operating system would first check its in-memory file cache for requested data. If the data is not in file cache, it sends the I/O request to the storage media. Data from the storage media is then written to the file cache, and then it is copied back to the application's buffer. Okay, now the operating system prefetches file data based on access patterns from the application to reduce the application's I/O wait time. Applications can also advise the operating system on where to prefetch and when to prefetch using system calls like fadvice and read ahead. Now, the operating system can either follow or ignore the advice without informing the applications of its decisions. Okay, so in this talk, we'll see how this lack of visibility between the application and the operating system actually leads to low I/O performance. Okay, we'll look at the challenges with I/O prefetching on modern storage today. Okay, so this is the meat of the presentation. So we take care of this. Okay, so what we see here is the cache state of a file where each white box represents a 4 kilobyte block of the file. Okay, the cache is empty right now. When I say purple blocks, that means the blocks are in file cache, and shaded blocks mean that the application advised them to be in the file cache. Okay, now let's say the application issues a prefetch advice for 4 pages starting at page number 1. The application can choose to prefetch only 2 pages from this advice. Now, this under prefetching could be due to various reasons, for example, memory pressure or hardware limitations. Later, the application could issue another prefetch advice for 2 pages starting at page number 5, and the operating system could choose to prefetch all the requested pages. Okay. Now, at this point, the application believes all 6 pages are in memory, while in reality, 2 pages are not in memory. Okay. Now, if the application issues a read on one of the 2 pages, that would be a cache miss instead of a cache hit, which means the application would have to wait for the data from the storage media instead of memory. Now, this is a loss in I/O performance. The OS could also choose to prefetch more than what was requested by the application due to prevailing access patterns, for example. Okay, here is the same cache state. The application issues a prefetch for 3 pages starting at page number 1. The operating system would take a reader's lock on the file cache, and it would go check the requested pages and find that none of the pages requested are in cache. So let's say it decides that I need to prefetch 5 pages. So it takes a writer's lock on the file cache and then populates the data to the cache. Okay. Now this decision to over prefetch was not told to the application. So it might prefetch, it might give a request for another page at page number 5, which is already in memory, but the application does not know about it. The OS has to still take a reverse lock to the cache and check the cache occupancy. Now, let's say when this is happening, another application thread issues a read system call on an unrelated block in the file. Okay. Now, this would have to wait for the cache check to finish for the prefetch. Okay. Now, this would also result in I/O throughput loss because of blocking overrides. Okay. To analyze this, we take a 1 terabyte NVMe SSD on a local system with ext4 file system, and we run RocksDB's batched random reads with 32 threads. Okay, we choose RocksDB particularly in this example because it issues prefetch request to the operating system and it is considered a well-tuned application. Okay, and we compare 3 prefetching approaches. The first approach is called app-assisted prefetching, where the application advises what to prefetch to the operating system. OS prefetching, where the OS decides what and when to prefetch, and there is no application advice to the OS. And CrossPrefetch is our approach, which I'll be talking about in a bit. We plot cache misses that are experienced by RocksDB. And here on x-axis, you have the different prefetching methodologies. Y-axis is the percentage cache miss. What we observe is that even with all the prefetching systems available, RocksDB is still seeing a huge number of cache misses, which would manifest themselves as low throughput to the application. Okay, and with CrossPrefetch, we try to alleviate this issue, and I will explain how. Okay, but before I get into our design, I'd like to stress that while there has been a lot of work on prefetching, using machine learning techniques, for example, or compiler techniques, which improve prefetching logic, to the best of our knowledge, none of these works actually address the lack of visibility. Okay, and CrossPrefetch does exactly that. It divides the prefetching responsibilities between the operating system and the application to ensure the best of both worlds in terms of performance and system stability by providing cache visibility to the user space. Okay. Okay, so let's look at how the design seems now. Again, it is a cross-laid approach. So you have 2 portions of the implementation, the cross-laid and the cross-OS. The operating system is responsible for providing the cache visibility to the application space, and the user space uses that to effectively prefetch. Okay. Now, CrossPrefetch requires no changes to the application because all the interface changes are actually handled by a runtime library transparently. Okay, let me go through these design aspects in depth. To provide cache visibility, we implement a new system call called read-ahead info, which is very similar to the read-ahead system call, with one key difference. Okay. In addition to doing fetch advice to the OS, it also gets the current file cache state and the current system memory pressure from the operating system. Okay. Again, no application change is required. Applications are free to change themselves, but they don't need to change because all the changes to the system call are handled transparently by the runtime library. The cache state is implemented as a bitmap, where each bit represents a 4 kilobyte block in the file. And so each operation on the file cache updates the bitmap using simple bit operations. Okay. Now the bitmap is memory efficient because for a 1 terabyte file, you need a 32 megabyte bitmap. This cache state is then now exported to the user space, and now it can avoid these issues mentioned earlier due to lack of cache visibility. For example, it can now query the cache state and only send prefetch advice for blocks that are not in memory. This will also help user space to implement custom prefetching policies based on its requirements, and they will be precise because you will already know what data is in memory or not. There are some features that I'm not going to depth today. I'm only going to introduce them for brevity. So, for example, CrossPrefetch supports concurrent prefetching for shared files by using range locks on the cache state. It supports aggressive prefetching and eviction mechanisms based on current memory pressure. CrossPrefetch also identifies sub-assumptions taken in the OS file subsystem implementation that limits prefetching on modern storage. Please read our paper for more information. Okay, now let's look at experiments. We asked 3 questions from CrossPrefetch. Does it improve IO throughput for different access patterns? Does it scale well with number of threads? And does it perform well with different memory budgets? Okay, so again, it's the same experimental methodology I introduced earlier, and we run RocksDB with 15 million keys and 4 kilobyte values, and we run dbench and YCSP. For the first plot, we see the IO throughput for different access patterns. So x-axis is the different IO access patterns, and y-axis is the throughput. And so we see that for some access patterns, for example, read sequential, the operating system prefetching approach would work better than even app-assisted prefetching because the OS is really good at identifying and prefetching sequential reads, for example. Okay, we observed that with CrossPrefetch, we improve up to 3.7x in IO throughput and around 2x on average. The next, we look at scalability. So here on x-axis, you have the number of threads on RocksDB, and y-axis is again throughput and 100 KOPS per second. And we observe that CrossPrefetch scales well with the number of threads as well. To understand how CrossPrefetch works with different memory budgets, here on x-axis, we have the memory budget as a ratio of the size of the database. So for example, if the size of the database is 100 GB, 1:2 would mean memory budget is 50 GB, for example. Okay, and y-axis is throughput again. And we see that while reducing the memory budget drops the average throughput, CrossPrefetch is able to extract 60% more on average from the system. Okay, in summary, we have shown that current IO prefetching is ineffective for modern storage due to lack of cache visibility and concurrency bottlenecks because of those. CrossPrefetch alleviates these challenges by providing prefetching responsibilities between the OS and the user space, and we show up to 3.7x performance benefits on even well-tuned applications. In conclusion, we observe that application performance could be lacking because of conflicting activity between the OS and the user space, and this is because of lack of communication that leads to incorrect presumptions at these layers. Okay, sharing information on a need-to-know basis might improve harmony in the system, which would improve the system performance at large. Okay, we have open sourced our code, so you can take a look at it. The QR code takes you to the GitHub page, and my co-author Jian is on the job market, so please scoop him up. Thank you so much. I'd be happy to take questions.
Hi, Michael Giordino, Huawei. I'm gonna do the annoying security thing and ask, does requesting this info from the OS introduce any potential security problems?
Very, very good question. So there's a class of security problems called side channel attacks. And so what we see here is two things. First thing is you only get access to file data or cache data for files that you have access to. Okay, so if you can open the file, you can see the data, right? That is one. Second is that there already exist system calls that give you this information. The only problem is that they don't write when you ask them. Okay, so we're not increasing the surface of the security problems. Yeah. Any other questions?
I had one quick question. I was wondering if when you have a lot of different prefetch requests, would you like some kind of prioritization mechanism to understand, what's more important than others?
Right. So here again, while the prefetching requests are given by the application, the OS is still king. It decides what to prefetch, what not to prefetch. It can be for really obnoxious applications, it can say, okay, I'm not prefetching anymore. So yeah, those are handled by the operating system as is. The only problem is that because it is not visible to the application, they might be losing performance out of that. Yeah, amazing. Yeah, good questions.
Thank you.
Yeah. So that's this one.
Right.
There's something to write.
Maybe use this one. Maybe it's not working.
Okay, so we already switched the computer before the session because my computer was not working. So I had to cite it. So there are some instructions encoded.
It's a good thing this isn't the reliability session.
I don't know what's happening.
Oh,
nothing is happening.
All right. It's Mr. Andre Griffin, member from Mines in Turkey, who has 25 years of experience in storage systems, and will share some of that story with us today.
Yes, and I'm happy to present Palantir, which is a hierarchical resemblance detection system for post-deduplication delta compression. And this is joint work with Hongming Wang, Peng Wang, Jiangzhu, Hongzhu, and Shun Jason Xu. And I'm pretty sure that I pronounced it not correctly. And you might guess that my name on this list is Andre Brinkmann, the only non-Chinese name. So what are we working on? We're working on backups. And in principle, one of the main goals when you're running a backup system is cost and cost efficiency. And this was the reason that for a long time, tape was the only backup medium which was really cost effective enough to be used. Then in 2007 or around 2007, people invented deduplication for backups. And what is deduplication doing? Deduplication is able to detect identical blocks in a huge data set and then to simply store it only once. You see here the example, we have A, B star, and then you only have to store A, B, and B star. So this already helps a lot. And if you do a lot of additional compression around it, then tape becomes really cost efficient. So again, it's about money, and you want to store as few information as possible without losing anything. Therefore, around 5-6 years ago, people started to say, okay, after this deduplication step, there are still a lot of blocks which are not identical but similar, and we can do some kind of delta encoding on top of them. And this is an additional step I will be mostly talking about today. It's about delta compression. The main key question about delta compression and delta encoding is how to find similar blocks. because of course I cannot compare with all of them. I can only compare with as few of them as possible. And therefore people don't, of course, do a greedy brute force search with all existing blocks. They have more or less adapted a kind of a super feature approach. And what are super features? In principle, I'm chunking, or I'm running the window over my data block. For each window, I'm more or less computing some kind of hash function, and I do n independent of them. And afterwards, from each of these hash functions, I just take the minimum value. And each of these minimum values of these n independent hash functions is one of my real features, which I want to use. So again, comparing against a lot of features takes a lot of time. And having just a single feature in common often means that there is not too much similarity. Just having one feature in common can mean nothing. And therefore, we use Broder's theorem, which says, okay, if I just combine a number of features to super features, and these super features are matching, then there's a really high probability that the blocks are very similar. And this is called a super feature-based approach and a transform approach, and it's widely used in research and most probably also in production. So what have we got to do? We are storing these super features in some hash tables. Then we do some lookups. We have k of these features, and in principle, this can lead to at most k lookups. And for each hash table and for each hash value, I store only the most recent one. So it can happen that the same super feature is existing for multiple blocks, but I always only store one. Because if I have to compare against 10 blocks, 12 blocks, which is really the most similar one, again, too expensive, takes too much time. So what is the drawback of existing approaches? In principle, I already told you we have features, and I assume we have around n features. And I combine them into k super features, and each super features is composed out of s features. So therefore, we have n, k, and s. And in principle, this is a trade-off. If I have too many features per super features, then it can happen that I don't detect similar blocks. Because this is a blue curve that you see on the right, where I have four features per super feature. And what is happening is I'm really detecting nearly all of the blocks which have around 90% similarity. I'm only detecting around 50% of the blocks. Now I have to look, which have around 65% similarity, and so on. And if the similarity decreases, then of course the probability that I really find my block also decreases. So what could I do? I could lower my S, so I could have less super features per super features. Sorry for that one. And then it can happen. Okay, I have this orange line. I detect more. This is helpful, but this also means that I detect more of blocks which are not really similar. And it can even mean that I first detect a block with a very low similarity, but I miss one with very high similarity. And therefore, the trade-off typically is that we take a lot of features per super features and therefore miss a lot of opportunities. How big is it? So we did some brute force analysis, and we compared 3 existing approaches called N-transform, finesse, and Odess with an optimal brute force algorithm. Of course, we were only able to do this on a small data set, but what we've seen is that we detect more or less 50% less similar blocks than what is possible in an optimal scenario. And also the compression ratio is much smaller than what is optimally possible. What is now our approach? We want to design a flexible similarity detection algorithm that finds more similar blocks than the state of the art without sacrificing the detection quality. How do we do this? We do a tiered approach. And just believe me, all approaches at the moment use n features, and n is 12, and 12 is a fixed number for reasons I don't discuss here. We can do this offline. And they more or less combine them into 3 super features. What we did, 12 has a nice feature that I could also combine it into 4 super features with 3 features per super features, and I combine it into 6 super features. And what I then do, and this is more or less the main first ingredient of our approach, is that I first check against the blue line, against the three superfeatures. Then if I don't find anything, then I compare with the orange line. And then if this is not working, I go back more or less to this gray line and try to find the rest. So, and what this helps us with is that, of course, first, we find all the really good matches, because in the first round of our algorithm, we do exactly what the rest in the state of the art is doing. And only if we don't find something, then we go a little bit to the lower quality blocks and go on and go on and go on. This always sounds simple, and we ask ourselves, why has the state of the art not done the same? And we found a few reasons for doing that and for not doing this. The first is, of course, as soon as you start to decrease the number of features per superfeature, you find a lot of blocks which are not really matching well. And you have to filter them out first. And you have to filter them out first without really being expensive. You have to be computationally inexpensive. And therefore, we defined a false positive filter in our approach, where we said, okay, let's check how good is the lossless compression of the matching block, which we found. Then we compare it with the average compression we have in our setting over the last H blocks. And only if the compression of this data encoding approach is better than the average compression we have, then we say, okay, it's a positive, we can take it. And this works out pretty well. And we have been able to show in our papers that this is even optimal for a greedy approach. Second point is metadata. So if you want to save and storage, then of course, it is counterproductive if you have to store a lot of metadata. And in principle, we have to store 3 superfeatures for our first tier. We have to store 4 superfeatures for the second one and 6 for the third one. So we have an explosion of superfeatures. This is not good. This is costly. And so what we did is we introduced a kind of metadata lifecycle management. So we said, okay, the best storage compression is achieved from the tier 1. This was sure from the beginning. Then tier 2 features are helpful, and tier 3 features are not that helpful. And what we did is we kept these tier 1 features forever. Tier 2 features are thrown away after 5 or 6 iterations, and tier 3 features are thrown away after 2 iterations. Okay, this is helping. So we built 5 synthetic data sets, which have been based on real backup data. We have used a Linux code repository, and we have compared with this in-transform algorithm with Finesse and with ODES. So is it helping? The most important thing is the end-to-end compression ratio, which we achieve. And we compared and more or less averaged everything to Finesse, which has had the worst compression ratio. And we see that compared to Finesse, we can really improve by 27% average over all data sets. And compared to N-Transform and ODES, which have a pretty good compression ratio, we can still improve by more than 7%. What is the reason? Because we find more similar blocks, of course. It's obvious, and therefore our detection rate becomes higher. Even, of course, it's the average compression per block is a little bit lower, because we also find these less well-matching blocks. What is the impact on throughput? The impact of throughput is mostly hidden by the pipeline design, which you have in modern backup systems. Therefore, you see that we have around 7% less throughput than the best performing approach, ODES. But again, we think that we even can hide this 7% so that we can come to the same performance as the state of the art by also detecting better matching blocks. So if you check this for different data sets, then you see that this is not only working well for one data set, it's more or less working for all data sets we have investigated. The Linux data set is a little bit special, because more or less it's a complete data compression we do against the last tier, because if a source code is checked in, its similarity is the best with the previous version of the source code. This is what you see here. Here you see also what are really the contributions. And there's a big contribution from deduplication. Then there comes a standard delta compression. Then you see what is happening with tier 1 delta compression. And finally, you can also see what is achieved by our additional compression tiers, and also by the false positive filter. And that this false positive filter is also really required. What is metadata analysis? So in principle, by our metadata lifecycle management, we achieve that our metadata is not exploding, but only around 30% higher than the state of the art. And we say, okay, this 30% higher is something we can pay for. And this is also already part of the comparison which you see here. So we have included these 30% more metadata into our comparison here. Finally, the sensitivity, of course. If you do some kind of delta encoding and delta compression, then in all cases, you have to know how much has really changed, which blocks have changed by how many percent. And this is something where we had to do a little bit of guessworking because there are absolutely no data set in the wild where you can really check against. So we did some kind of parameter and sensitivity analysis, and we said, okay, we change a little bit the fraction of blocks which are changed per iteration of the backup. We change how much data per block is changed. And in all cases, our achievements remain pretty stable over time. Of course, they're a little bit fluctuating. Sometimes it's 4% what we are better, sometimes it's 10% what we are better, depending really of the changes. And so in summary, we have presented Palantir, which is a framework to improve data compression within backup environments. Really important components are this adaptive false positive filter and also our metadata lifecycle management system. And end-to-end compression really got better, but still there's a lot of future work. One is really becoming faster, having a pipeline design which really embraces our changes. And the second one is we are really looking for real-world data sets that we can say, so it's really 1% is changing, 10% is changing. We really don't know at the moment. We have to guesswork here. And therefore, thank you for the time and happy to take questions.
Andreas Koch, TU Darmstadt. As for getting faster, have you thought about putting this in hardware? FPGAs do hashing extremely well, and that can be significantly faster than 178.
Really agreed. And the fun thing is that the hashing is not in our critical path anymore. So there is a wonderful invention which was by Odess, which has been published in 2021, where the people said, okay, we don't have to hash every more or less window in our data block. We can just take a few of them, and by correctly selecting them, more or less, we come to exactly the same conclusions concerning compressibility. And therefore, this is people worked a long time on really getting this hashing out of the critical path. With your approach, it might be not necessary. I agree.
So what is a critical path then, if I may ask, if hashing is no longer on it?
This is very dependent. So we have parts of the deduplication component which lock parts of what we do. And therefore, we really have to wait for this deduplication component. And in principle, if we have our pipeline designs and slightly rearrange it, then we can get rid of it. But of course, this was a lot of code we had here, and it was not the main focus of our approach to say, okay, it's the fastest in the world. At the moment, we wanted to be just the most efficient one.
Yeah, I still think there is potential for hardware acceleration.
Yes. So there was just one comment to the potential. There was one follow-up paper to the Odess approach, so which was not by us. And they at least used AVX to improve the linear transformations, which is not the hashing itself, but which helps a lot here. And they've seen an interesting speed up there.
Hi, Emil, Tsalapatis, Waterloo. If you use cheaper features right now with the combinations that you have, could you do this online for other kinds of workloads? Because right now this seems like it's for tape and it's for essentially going to maximize your gains. Could you use something that is possibly less accurate and possibly has more false positives, but make it cheaper so that you can use it in other fields?
So we use it for disks. So from that perspective, I don't see that. How would you do it?
Oh, I'm asking essentially, it seems like the overhead is the features themselves, right?
No, there's the features. And so it's really the overhead we have here. So of course, you have to check. You have to do the delta compression, which is expensive. You have to load the base block you compare with. So you have additional IOs which you introduce. So there's a lot of overhead which we cannot get rid of And again, the hashing itself and the feature generation has been in the critical path in the past. So this was the reason that this finesse approach in 2017 has been introduced. And at the moment, it's really a lot of overhead you cannot easily get rid of.
I see.
So I think we have written a little bit about it in the paper. So please take a look, and of course, happy to discuss it afterwards.
Thank you.
Okay, that concludes our session. There will be buses to the museum, leaving in about 10 minutes, I think, from the